So, in this lecture, we shall learn how to view metric spaces uh, as topological spaces. So, we shall also see an equivalent and more intuitive criterion for continuity of maps between metric spaces. So, let us begin by recalling the definition of a metric space. So, let X be a set and let T from X cross X to the non-negative real numbers. So these real numbers which are greater than or equal to 0 be a function which satisfies the following conditions. So the first condition is that if you take 2 points x and y, so then d of x comma y is 0 if and only if x is equal to y. The second condition is that this d is symmetric, so the distance between x and y is equal to the distance between y and x. The third condition is the triangle inequality. So that's distance between x and z, any 2 points is less than or equal to distance between x and y plus distance between y and z. So this is for all x, y, z in x. And this is called the triangle inequality. So the map D is called a metric on X. So it defines a notion of distance between points of X. So the most common example of metric spaces that we see we encounter is Rn with the Euclidean metric. So that is, so for 2 points, let's say x bar, the distance is defined to be half. So here obviously x is this n tuple and y is this n tuple. So let us check. So there's something which uh, is must have been familiar or done in a real analysis course, but let's just check this once again. So let us check that this defines the metric. So the first two conditions are obvious to check. We only need to check that it satisfies the triangle inequality. So we only need to check that triangle inequality is satisfied. So for simplicity of notation, for any x and y in Rn, let us write this is defined to be this distance between x and y. So proposition is that this satisfies triangle inequality, that is x minus y. So how do we prove this? So first we make a simple observation. It is enough to check that for all x and y we have norm x. Because if we can check this, then we can put x equal to x minus z and y equal to z minus y. Well, yeah, let me write this x plus y. So if we put x equal to x minus z and y equal to z minus y, then we get exactly the statement of the proposition. So let us check that this is true. So for this, right, so consider, so we define an inner product or consider the map Rn cross Rn to R. This is defined by x comma y maps to the inner product of x and y. This by definition is to n xi yi. So we first claim that the absolute value of this inner product is less than or equal to the norm of x times the norm of y. So to see this, let us write w is equal to y minus t of x, where t is some real number. So w is a vector in Rn. So x and y are fixed. W is this vector in Rn which depends on x, y, and t. So then the inner product of w with itself is equal to y minus tx comma y minus tx, and this is equal to, since the inner product is bilinear, t into y comma x minus t into x comma y. Now inner product is also symmetric in x and y. So this we can write as right. So well, for a fixed x and y, if we view this as a quadratic form or a quadratic polynomial in T, let's say a quadratic polynomial in T, then as so this inner product of w comma w, this is always greater than or equal to 0. So here we just plug in the definition of inner product. So therefore we see that this, for all values of t, this quadratic form is always greater than or equal to 0, which implies that the discriminant should be less than or equal to 0. It follows that the discriminant is less than or equal to 0. But the discriminant is b square minus 4ac. So this implies that is less than or equal to, so there is a 4, which implies that which is what we had claimed. So this proves the claim. So from this, okay, so now we will use this claim. So from this we get, so this is just the definition. This is the inner product of x minus y along with x minus y. So this is equal to, so here we have used that the inner product is symmetric, and this is less than or equal to, which is less than or equal to, which is equal to, so this implies that so if we replace y by minus y in this, so we will get that. Because we can check using the definition that the norm of y and minus y are equal. So this shows that, so this implies, so thus is a metric space where d of xy is equal to this. So given a bit, so okay, so we have defined a metric space and we have seen the most important example of a metric space. But what we want to do is, given a metric space X, we can use the metric to define a topology on X. So we define it as follows. So first, for any epsilon positive and x in X, we define the epsilon ball is those y in X such that there's those y whose distance from X is strictly less than epsilon. So now consider the collection B in power set of X defined as, so B consists of all these epsilon balls where epsilon is positive and X is in X. So it is easily checked that B satisfies the two conditions for being a basis. Thus, B defines a topology tau on X and B is a basis for tau. But we can be even more explicit about what the open subsets in X are. So it is easily checked that a subset U contained in X is open if and only if it satisfies the following property. For every X in U, there is an epsilon positive such that B epsilon X is contained in U. So for every X in U, there is an epsilon positive such that there's a small ball around X which is completely contained inside U. So this is like the property star which we use to define the standard topology on R or Rn. So yeah, so it is trivial and this is left as an exercise to check that the topology defined by the Euclidean metric on Rn is the standard topology. So next, we see a criteria for in a metric space of how to say some subset is closed or how to say that some point is in the closure of a set. So let X be a metric space and let Xn n greater than equal to 1 be a collection of points of X. So we say that Xn converges to X and we write it as Xn converging to X if for every epsilon positive there is and n such that xn belongs to b epsilon x for all n greater than equal to capital N. So what we want is that no matter how small a ball we take around x, so after finitely many xn's, all the xn's should be inside this ball. Okay, and we have this useful lemma which we will use to prove our next theorem in the proof of our next theorem. So let X be a metric space. And let A containing X be a subset. Then X belongs to the closure of A if and only if there is a sequence xn which converges to X with and so there is a sequence of xn's in all the xn's are in A and xn's converge to X. So let's see a proof of this. So let's assume that X belongs to a closure. So by definition of closure, every open set U which contains X meets A. So in particular, take U to be equal to B 1 upon n x. So we take the ball of radius 1 upon n around x and and choose. So since x is an A closure, this ball it meets x and choose any point xn which is in the intersection. So we choose any point which is in the intersection of this ball with A and we call it xn. So then it is clear that xn converges to x. So this is just a easy check using the definition of convergence. Right, and all the xn's also belong to A. Okay, so now let's prove the converse. Conversely, suppose xn's converge to x and xn's are in A. So then we need to show that x is an A closure. So for that, let U containing x be an open set. Then there is epsilon positive such that b epsilon x is completely contained inside U. So as xn converges to x, there is n such that for all n greater than equal to capital N, the xn's belong to b epsilon x. So this shows that, so the xn's are also in A, so thus b epsilon x intersected A is non-empty. So this implies that U intersected A is non-empty. So this implies that x belongs to A closure. So this proves this lemma. And finally, so using this lemma, we will prove the main theorem which we wanted to prove. So theorem. Let x and y be metric spaces. let f from x to y be a map of sets, then f is continuous if and only if for every sequence xn's converging to x. So we take any sequence of xn's which converges to a point x in capital X. So we have f of xn's converge to f of x. So let us prove this. So we first assume that f is continuous. So this implies that, okay, so for epsilon positive, so then we start with the sequence xn converging to x, and we have to show that f of xn converges to f of x. So we take any epsilon positive and consider the open ball. So since f is continuous, so this implies that the inverse image of this ball is open in x, and clearly it contains x. So thus, by the definition of the topology defined by the metric, there is a delta positive such that this b delta of x is contained in f inverse of b epsilon of x. So as xn's converge to x, there is n such that for all n greater than or equal to this capital N, xn's belong to b delta of x. So this implies that f of xn belongs to b epsilon f of x for all n greater than or equal to n. But this is just exactly the definition of f of xn converging to f of x. So we have found a capital N such that for all small n greater than or equal to capital N, f of xn converges to f of x. So this proves one implication. So now let us prove the converse. So it suffices to show, so to prove that f is continuous, it suffices to show that the inverse image of a closed subspace, of a closed subset Z contained in Y is closed. So we have a new criteria to show that a space is closed in a metric space. So we will use that. So recall from the previous class, from the previous lecture, that Z is closed if and only if Z is equal to Z closure. So thus, to show f inverse Z is closed, enough to show that it is equal to its closure. So let us pick a point in the closure. So by the criterion which we saw in the previous lemma, so this implies there exists a sequence containing f inverse z such that xn converges to x. And since xn is converging to x, by our hypothesis on f, this implies that f of xn converges to f of x. But now f of xn is in z, and z is equal to z closure, and z closure is contains all those points which have for which a sequence in z converges to that point. So in particular, so this implies that f of x belongs to z closure, which is equal to z, as z we are assuming to be closed. So we have proved that f of x is in z, which is same as saying that x belongs to f inverse of z. So thus we have proved that f inverse z is equal to f inverse z closure, which is same as saying that f inverse z is closed. So this implies that f is continuous. So we will end the lecture here.